And what I hope to do is, I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Now, what's the doubling time for 7% growth? 10 years. There's something else that's very important. The growth in any doubling time is greater than the total of all of the preceding growth. Every time the growing quantity doubles, it takes more than all that you'd used in all of the preceding growth. Now let's look at this in a very nice graphical way. Suppose the area of this tiny rectangle represents all the oil we used on this earth before 1940. Then in the decade of the 40s, we used this much. That's equal to the total of all that have been used in all of history. In the decade of the 50s, we used this much. That's equal to the total of all that have been used in all of history. In the decade of the 60s, we used this much, and again, that's equal to the total of all the preceding usage. Now, here we see graphically what President Carter told us. Now, if that 7% had continued through the 70s, 80s, and 90s, there's what we need. But that's all the oil there is. Now, there's a widely held belief that if you throw enough money at holes in the ground, oil is sure to come up. Well, there will be discoveries in new oil. There may be major discoveries, but look, we have to discover this much new oil if we would have that 7% growth continue 10 more years. Well, ask yourself, what do you think is the chance that oil discovered after the close of our class today will be in an amount equal to the total of all that we've known about in all of history? And then realize if all that new oil could be found, that would be sufficient to let the historic 7% growth continue 10 more years. Now let's see what it means. It means that from now on, domestic oil production can only go downhill, and it's downhill all the rest of the way. And it doesn't matter what they say inside the Beltway in Washington, D.C. Now it means we could work hard and put some bumps on the downhill side of the curve. You'll see there are bumps on the uphill side. The debate is heating up over drilling in the Arctic Wildlife Refuge. I've seen the estimate that they might find 3.2 billion barrels of oil up there. 3.2 billion is the area of that little tiny square. That's less than 1 year's consumption in the United States. Now, let's look at the curve in this way. The area under the entire curve represents the entire resource of U.S. petroleum before any of it was used. Now, that area has been divided here into 3 parts. Unshaded on the left, that's the oil we've taken from the ground. We've used it, it's gone. This vertical shaded band, that's the oil we've drilled into. We've found it, we're pumping on it today. Shaded in green on the right is the undiscovered oil. We have very good ways now of estimating how much oil remains undiscovered. This is the undiscovered oil. This is the oil we're looking for in all those places where drilling is going on. This is the oil we've got to find if we're going to make it down the curve on schedule. So maybe you're wondering, well, why didn't somebody tell us this? It was back in 1956. Dr. Hubbard addressed a convention of petroleum geologists and engineers. He told them that his calculations led him to conclude that the peaks of U.S. oil and gas production that you just saw can be expected to occur between 1966 and 1971. No one took him seriously. So let's see what's happened. The data here are from the Department of Energy. So this is U.S. oil production. We see a long period of approximately steady growth. Here's the year 1956 when Dr. Hubbard did his analysis, and he said at that time that the peak would occur between 1966 and 1971. Well, the peak occurred in 1970. It was followed by a very rapid decline. Then the Alaska pipeline started delivering its first oil, and there was a partial recovery. That production has now peaked, and everything's going downhill in unison. And one of Dr. Hubbard's favorite graphs is this one. And this is on a time scale from 5,000 years ago to 5,000 years in the future, and the age of fossil fuels is a little blip in the middle of the screen. Think about it. Well, we have to ask about new discoveries. Here in 1993, we read about the largest oil discovery in the Gulf of Mexico in the past 20 years, an estimated 700 million barrels of oil. Now that's a lot of oil, but a lot compared to what? At that point, we were consuming in the United States 16.6 million barrels of oil every day. Do the long division and you find that entire discovery would serve our needs for 42 days. And that's the biggest discovery they've made in the Gulf of Mexico in 20 years. Let's take another look at world oil production. Now the graph here is slightly different from the one I showed earlier. What I'm showing here is per capita production of oil, which means that at every point I take the world production divided by the world population that year. Now the scale here on the vertical axis is liters per person each day. There's the number 2. Now 2 liters a person a day. 2 liters is about half a gallon. Now notice that the peak occurred in the 1970s, and it's been going downhill, and in the 1970s it was a little over 2 liters a person a day, and now it's down to about 1.7 liters per person each day. So we can say with confidence that any day that any one of us uses more than 1.7 liters of petroleum directly or indirectly, we're using more than our share. Now what's the average consumption in the United States? And the answer is it's up around 8 liters a person a day. So think about the inequity that's represented there. Now there's something even more important in this graph. That peak in the 1970s, I think that historians in the future will look back at this peak and say that was a major turning point in all of human history. That's the point where per capita consumption of petroleum reached its peak before it started its inevitable decline, and there isn't any way I can see that we can reverse that trend, that downward trend, given the world population growth and given the fact that we're right close to the peak of world production. And of all the crises, I think this one, global warming, looms larger and more threatening than anything in all of human history. Now, because of our enormous per capita consumption of resources, we can say with confidence the world's worst population growth problem is right here in the United States. But you hear all sorts of well-meaning people pointing to distant underdeveloped nations and saying they're the problem with overpopulation. The average person in the United States in a lifetime will consume something like maybe 30 times the amount of resources that'll be consumed by a person in a lifetime in an underdeveloped nation. We are the problem. We have the responsibility, and we have the authority to deal with the problem here as a domestic problem in the United States. And if there was ever a time when the human race needs people who will think, it's right now. It's our responsibility as citizens in a democracy to think. And so to be successful with this experiment of human life on Earth, we have to understand the laws of nature as we encounter them in the study of science and mathematics. We should remember the words of Galileo. He said, "I do not feel obliged to believe that the same God who has endowed us with sense, reason, and intellect has intended us to forego their use." And so I hope I've made a reasonable case for my opening statement that I believe the greatest shortcoming of the human race is our inability to understand this very simple arithmetic.